A supernova tears a star apart. From that chaos, a new kind of monster might be born. Not a black hole, not a neutron star, but something far stranger. This is the realm of quark stars and strange matter, where the universe's most basic building blocks are forced into impossible configurations. By the end of this journey, you will understand 25 profound mysteries that could rewrite the laws of physics. What if a single speck of this strange matter could unravel our entire world? And what cosmic signatures are we missing, simply because we do not yet know how to look? How much of the universe remains hidden, waiting for us to ask the right questions? The first and greatest mystery is whether they exist at all. We have mountains of evidence for neutron stars, those city-sized remnants so dense a teaspoon of their material would weigh as much as a mountain. We have even more indirect but compelling proof for black holes, the ultimate gravitational traps. But quark stars remain in the shadows, a theoretical possibility born from the equations of extreme physics. They are not a certainty, but a stunning prediction of what might happen when you push matter beyond the neutron star's breaking point. Picture a neutron star already unimaginably dense. Its own gravity is so powerful that it has crushed atoms into a sea of neutrons packed shoulder to shoulder. But what if the pressure increases even further? The theory suggests that at a certain critical threshold, the neutrons themselves can no longer hold their structure. They shatter, they dissolve, their boundaries break down, and the particles inside them, the quarks, are set free. This is the quark matter phase transition. It is not like ice melting into water, but something far more fundamental. It is the moment the universe's building blocks are forced into a new state of being, a soup of up, down, and strange quarks flowing freely. This strange matter would be the most perfect, stable substance in existence, a state matter naturally wants to be in under such extreme conditions. The problem is confirmation. How do you see something that, by all theoretical accounts, would look almost identical to a neutron star from a distance? Both would be small, incredibly dense, and spin rapidly. The differences are subtle, hidden in the details of their size, their cooling rate, and the way they vibrate. A quark star might be slightly smaller and cooler than a neutron star of the same mass, a tiny signature lost in the vastness of space. This makes quark stars the potential missing link in stellar evolution. They could be the final stable state before matter collapses into a black hole's infinite darkness. Finding one would not just add a new object to the cosmic catalog. It would prove that nature takes this exotic path, that under the greatest pressures, the universe chooses to unlock the quark. This leads us directly into the second and perhaps most unsettling mystery. What if everything we are made of is not the most stable form of matter in the universe? This is the radical premise of the strange matter hypothesis. In our world, the protons and neutrons inside every atom are built from two types of quarks, known as up and down quarks. They are the familiar building blocks of reality, but the quark family has a third, heavier, and more exotic sibling, the strange quark. Under normal conditions, strange quarks are unstable and decay almost instantly. However, inside the unimaginable pressure of a collapsing stellar core, something extraordinary could happen. Physicists Robert Bodmer and Edward Witten proposed a hypothesis that flips our understanding on its head. They suggested that a dense lump of matter composed of roughly equal numbers of up, down, and strange quarks, a substance called strange matter, might actually be more stable than the iron in the Earth's core or the carbon in your body. In this view, the atomic nuclei that form our world are not in their ultimate, lowest energy state. They are merely a metastable phase like diamond. Diamond is stable, but given enough energy, it wants to become graphite, a more stable form of carbon. According to this hypothesis, we are all diamonds waiting to be turned into graphite. A chunk of this perfect, stable strange matter is called a strangelet, And here is where the hypothesis crosses from fascinating physics into the realm of cosmic caution. If a strangelet is truly the ground state of matter, then what happens when it touches normal matter, like a proton or a neutron? Theoretically, it could convert that normal matter into more strange matter. The process would release energy and bind the newly converted particles to the strangelet, making it grow. This is the terrifying concept of the strange matter infection. A single, tiny strangelet, perhaps created in a quark star or a particle collision, could, in theory, begin converting any nucleus it contacts. It would not stop. It would transform a person, a planet, a star from the inside out, rewriting the very code of its material existence into this alien, hyper-dense substance. While this sounds like the plot of a science fiction disaster, it is a scenario physicists take seriously enough to have studied at particle colliders like the Large Hadron Collider. The consensus is that such an event is extraordinarily unlikely, but the fact that it is even a topic of scientific discussion underscores how profoundly strange this hypothesis is. It proposes that the universe might have a preferred, ultimate state for matter, and we are simply not in it. This theoretical uncertainty creates a profound identity crisis for any potential discovery. If we do find an object that defies the neutron star model, what exactly are we looking at? Is it a star made entirely of this exotic quark soup from its surface to its core, a pure quark star? Or is it something more complex, a celestial layer cake with a dense quark matter core wrapped in a thick shell of ordinary neutron star material? Astronomers call these theoretical objects hybrid stars. The distinction is not just academic, it is an architectural mystery that speaks to the very nature of matter under extreme duress. The answer depends on something called the equation of state. Think of this as the universe's recipe for how matter behaves when you squeeze it unimaginably hard. A soft equation of state suggests matter compresses easily, allowing a large quark core to form inside a hybrid star. A stiff equation of state implies matter resists compression, favoring a smaller quark core or perhaps preventing one from forming at all. Different equations of state predict different relationships between a star's mass and its radius. A pure quark star might be smaller and denser for a given mass than any hybrid star could ever be. So how do we peer inside an object 10,000 light-years away to see its internal blueprint? We listen to its vibrations and watch for its stumbles. Neutron stars, and by extension their quark-filled cousins, are not perfectly smooth spheres. They have mountains, crustal faults, and internal currents. Occasionally, the rigid crust of such a star will suddenly crack and shift in a starquake, causing the entire object to spin faster in an instant. This event is called a glitch. The pattern of these glitches, their size and frequency, is a direct fingerprint of the star's interior structure. A glitch in a hybrid star would propagate through both a solid crust and a fluid quark core, creating a different seismic signature than a glitch in a pure quark star, which might have a very different kind of surface. Furthermore, when two of these ultra-dense objects spiral together and collide, they send ripples through the fabric of spacetime itself. These gravitational waves carry encoded information about the object's tidal deformability, essentially how squishy they are. A pure quark star, being supremely dense, would be very hard to deform. A hybrid star with a softer quark core might be more malleable. By comparing the gravitational wave signals from collisions to predictions from thousands of different equations of state, astrophysicists are slowly learning to distinguish one internal architecture from another. Each observation is like a sonogram of a stellar corpse, revealing layers we could never see with light alone. The search for these cosmic phantoms is not just theoretical. It involves staring at specific points of light in the night sky and asking, "What are you?" One of the most famous and frustrating candidates is a lonely star in the southern constellation Corona Australis, known as RxJ 1856.5-3754. Discovered by the Rosat X-ray satellite in the 1990s, this object immediately stood out. It was incredibly hot, glowing fiercely in X-rays, and it was completely isolated with no binary companion to steal matter from. Most intriguing of all, when astronomers calculated its size based on its temperature and distance, the numbers pointed to something astonishingly small. The initial data suggested a radius of only about 11 kilometers, roughly half the expected size of a typical neutron star. This tiny measurement, combined with the fact it emitted no regular radio pulses like a pulsar, sent a wave of excitement through the astrophysics community. Here at last seemed to be the smoking gun, a star so small and dense that it could not possibly be made of neutrons alone. It had to be something more compact, something where matter had been crushed into its constituent quarks. For years, RxJ 1856 was heralded as the best potential quark star we had ever found, a solitary beacon of exotic physics. The story, however, was not over. Science thrives on scrutiny. Later observations with more powerful telescopes like the Chandra X-ray Observatory revealed a subtle but critical detail. The star's X-ray spectrum showed a nearly perfect blackbody curve, meaning its light came from a smooth, hot surface. But if it had a normal neutron star atmosphere of hydrogen or helium, that atmosphere would imprint specific absorption lines on the spectrum like a chemical fingerprint. Those lines were missing. Researchers proposed a brilliant and simpler explanation. What if RxJ 1856 did have an atmosphere, but one so hot and incredibly thin it was almost a perfect blackbody emitter? A thin, solid surface of normal neutron star material, shrouded by this searing haze, could mimic the emission of a much smaller, bare quark star. This atmospheric model could reproduce the observed data without requiring a radical new state of matter. Just like that, the leading candidate faded from a potential revolution back into an enigma. The case of RxJ 1856.5-3754 is a masterclass in cosmic detective work. It shows how a single, tantalizing clue can point toward a universe-shattering conclusion, only for a more mundane explanation to lurk in the details. It underscores the immense challenge of identifying something that, by its very nature, strives to hide in plain sight, disguised as its more ordinary cousin. The fading hope for RxJ 1856 did not end the search. It simply shifted the focus from a single, quiet object to the most dynamic and violent laboratories in the universe. To understand the interior of these stars, we must listen for their stumbles. Deep within the Crab Nebula, the remnant of a supernova witnessed on Earth in 1054, lies a pulsar spinning 30 times every second. It is a cosmic lighthouse of breathtaking precision, yet on rare and unpredictable occasions that precision shatters. The pulsar's spin suddenly jumps, speeding up by a tiny but measurable fraction in a matter of minutes. This event is a pulsar glitch, and it is one of the most direct probes we have into the heart of a stellar corpse. For decades, the leading explanation involved the star's interior behaving like a complex fluid. A neutron star's outer crust is a rigid lattice of atomic nuclei, a solid shell kilometers thick. Beneath it, the core is thought to be a superfluid, a frictionless quantum liquid where neutrons can flow without any resistance. As the pulsar's magnetic field acts as a brake, slowing its rotation over millennia, the superfluid core, decoupled from the crust, does not slow down as much. It spins faster, storing rotational energy like a wound-up spring. The glitch occurs when this pent-up energy is suddenly transferred to the crust. A sudden cracking or rearrangement in the rigid lattice, a starquake, couples the superfluid to the crust for an instant. The faster spinning superfluid gives the crust a violent kick, and the entire star spins up in a heartbeat. But what if the core is not a neutron superfluid? What if at its very center lies a super-free quarks? A quark matter core would have profoundly different properties. its viscosity, its ability to flow, and how it interacts with the surrounding neutron material would all be alien compared to a pure neutron fluid. This changes the glitch mechanism entirely. In a hybrid star model, the glitch would originate not from a single, uniform superfluid, but from the turbulent boundary where the quark core meets the neutron mantle. The transfer of angular momentum would be messier, the recovery slower, and the size of the glitch potentially larger. The aftermath of a glitch is just as telling as the event itself. After the sudden speed-up, the pulsar's rotation gradually relaxes back toward its pre-glitch rate over days or years. This recovery is a fingerprint of the internal friction and vortex dynamics. A quark core, with its different density and interaction strengths, would leave a distinct signature in this relaxation curve. It would be like listening to a bell ring. A bell made of steel and a bell made of glass, when struck, will ring with different tones and decay at different rates. A glitch is the strike, and the star's subsequent spin is its ring. By meticulously measuring the precise timing of thousands of pulsar rotations before and after a glitch, astronomers are comparing the observed ring to theoretical predictions. Does the data better fit the tone of a pure neutron star bell, or one with a strange, dense quark core at its center? Each glitch is a seismic event that sends tremors through the star's entire structure, and by reading those tremors, we are learning to see inside an object we can never visit. The universe's most violent explosions might be hiding a secret ingredient. Among the catalog of supernova, a rare and baffling class stands out. They are called superluminous-supernovae, stellar detonations that can outshine an entire galaxy for months, radiating energy equivalent to billions of suns. The conventional model of a core-collapse supernova, where a massive star's iron core implodes into a neutron star, cannot explain this staggering output. The math simply does not add up. There is not enough radioactive nickel, the usual fuel for a supernova's bright afterglow, to power such a spectacle. So where does all that light come from? One radical theory points directly to the birth pangs of a quark star. Imagine the final moments of a supermassive star. Its core collapses, passes through the neutron star phase, but the inward crush of gravity does not stop. The pressure continues to mount, reaching a critical threshold where neutrons disintegrate. In a catastrophic instant, the entire core undergoes a phase transition from neutron matter to quark matter. This is not a gentle shift. It is a fundamental rearrangement of the universe's building blocks, and it releases a titanic second wave of energy. Theorists call this event a quark nova. Think of it as a supernova inside a supernova. The first explosion creates a neutron star, and moments later, as that newborn star's core collapses into an even denser quark star, a second, even more powerful shockwave erupts. This double explosion injects a colossal amount of energy into the expanding debris from the first blast, reheating it to incredible temperatures and causing it to shine with unnatural ferocity. This model elegantly explains the extreme luminosity and the unusual light curves, the patterns of brightening and fading, seen in some superluminous events. One famous candidate is supernova 2006 Gi, an explosion that peaked at a brightness 100 times greater than a typical supernova. Its light curve and spectrum defied simple explanation, requiring an energy source far beyond the norm. Could it have been the signature of a neutron star transforming into something stranger, a final, brilliant flash as matter was rewritten into its most stable form? While other explanations exist, like the interaction of the blast wave with a dense shell of previously ejected material, the quark nova remains a compelling and terrifying possibility. It suggests that the universe's most dazzling fireworks might not mark a simple death, but a strange and violent rebirth. The final, brilliant flash of a superluminous supernova is not the only way to witness a quark star's birth. There is another, more subtle signal, one written not in light but in the fabric of space itself. When two of these ultra-dense remnants spiral together in a final, fatal dance, they do not do so in silence. Their immense gravity churns the cosmos, sending out ripples that stretch and compress space-time as they travel. These are gravitational waves, and their unique sound could be the definitive proof we need. Instruments like LIGO and Virgo are not telescopes that see light. They are colossal microphones listening to the universe, and they have already heard the mergers of neutron stars. But what if some of those collisions were not between pure neutron stars? What if one or both contained a secret quark core? The gravitational wave signal would carry that hidden truth. The key lies in a property called tidal deformability. Imagine holding two soft, ripe peaches in your hands and bringing them slowly together. Just before they touch, their own mutual gravity will stretch them, making them bulge slightly toward each other. They are deformable. Now, imagine doing the same with two ball bearings made of solid steel. They are so hard and dense that gravity barely distorts their shape before they collide. They have very low tidal deformability. A quark star, especially a pure one made of that perfect, incompressible strange matter, would be the ultimate cosmic ball bearing. It would be incredibly stiff, resisting deformation almost completely. A standard neutron star, while still incredibly dense, is thought to have a slightly softer interior, more like a peach with an impossibly hard pit. It would bulge more easily in the intense gravitational field of its partner. This difference in squishiness leaves a clear imprint on the gravitational waves emitted in the final moments before merger. The signal from two stiff quark stars would look and sound different from the signal of two softer neutron stars. It would reach a higher frequency just before the final collision, and the entire waveform would be subtly shifted. For astrophysicists, each detected merger is like a unique chord played on a celestial instrument. By comparing the observed chord to a vast library of predicted chords from millions of simulated collisions, each using a different equation of state for the star's interiors, they can work backwards. They can ask which internal structure, which recipe of matter, best reproduces the sound we just heard. Did we just listen to two neutron stars merging, or did we witness the collision of two hybrid stars, their quark cores finally meeting? Or perhaps, in the most extraordinary case, the pure, clean ring of two true quark stars. Every new detection adds another data point, another note in a growing symphony that is slowly teaching us what these objects are made of. It is a direct, physical probe of matter under conditions no laboratory on Earth could ever recreate. We are learning to diagnose the hearts of dead stars by the echo of their collisions. But the echoes of a distant merger are not the only messengers from this strange frontier. For over a century, scientists have been bombarded by a rain of particles from deep space, carrying energies that defy all explanation. These are ultra-high-energy cosmic rays, atomic nuclei hurtling through the void with the kinetic energy of a professionally thrown baseball, all compressed into a single subatomic speck. Their origin is one of the great puzzles in astrophysics. No known process in our galaxy seems powerful enough to accelerate a particle to such insane velocities. Could the answer lie in the ultimate destruction of a quark star? This is the cosmic ray conundrum. When two quark stars collide, or when a quark star is torn apart by a black hole, the theoretical violence is beyond comprehension. The energies involved could be sufficient to not only create strange matter, but to blast fragments of it clear across the cosmos. These fragments would be strangelets, nuggets of that perfect, stable, strange matter. If they survived the journey and slammed into Earth's atmosphere, they would register as an ultra-high-energy cosmic ray event. But here is the catch. To our detectors, a strangelet would look almost identical to a heavy atomic nucleus like iron or lead. It would have a similar electric charge and mass. The difference is in the details of its stability and how it interacts as it plows through matter. A normal nucleus is a bundle of protons and neutrons held together by the strong nuclear force. A strangelet is a bundle of quarks in a fundamentally different configuration. As it travels, it might decay in an unusual way or leave a distinctive trail of particle showers in the upper atmosphere. The hunt for these ghostly fragments is underway on the very edge of space. The Alpha Magnetic Spectrometer, a massive particle detector mounted on the International Space Station, has been silently sifting through the cosmic ray flux for over a decade. Its purpose is to search for antimatter and dark matter, but it is also exquisitely sensitive to the signatures of exotic, heavy particles. It measures the charge, mass, and trajectory of incoming cosmic rays with unprecedented precision. Every so often, it detects an event that does not fit the profile of a known nucleus. The data shows a particle with the right charge to be something like iron, but it behaves just a little bit differently as it passes through the detector's magnetic field and layers of silicon sensors. Is it a rare isotope, a fragment of a distant supernova, or is it something never before seen, a piece of a quark star, a shard of strange matter that has traveled for millions of years to reach us? Each anomalous detection triggers intense scrutiny. Researchers must rule out every possible mundane explanation, from instrumental error to a rare nuclear interaction, before the whisper of strangelet can even be considered. The challenge is immense, turning every potential signal into a profound mystery. It means we might already have recorded evidence of strange matter in our data, but simply lack the definitive key to recognize it for what it truly is. The search for strangelets in cosmic rays points toward an even grander possibility. Could this exotic substance be hiding in plain sight, woven into the very fabric of the cosmos itself? This brings us to a breathtaking, if speculative, connection. Could some portion of the universe's missing mass, the enigmatic dark matter, actually be made of strange matter? For decades, the evidence for dark matter has been overwhelming. Galaxies spin too fast, clusters of galaxies bend light too strongly, and the large-scale structure of the universe points to the gravitational influence of something we cannot see. We know dark matter exists because of its pull, but we have no idea what it is. Most candidates, like WIMP or actions, are hypothetical elementary particles. But another class of candidates exists known as MACHO, or massive astrophysical compact halo objects. These are normal, baryonic objects like black holes, neutron stars, or brown dwarfs that are simply too faint to see. Searches for MACHO, however, have largely ruled them out as the primary component of dark matter. There just are not enough of them, but what if the objects are not normal at all? This is where strangelets enter the picture. In the furious first moments after the Big Bang, during the quark-gluon plasma phase, pockets of this primordial soup might have cooled and condensed directly into stable strange matter nuggets. These primordial strangelets would not be stellar ashes but relics from the universe's birth. They would be cold, incredibly dense, and completely dark. They would emit no light, no radio waves, nothing but the faintest whisper of gravity. A vast population of such objects drifting in the halos of galaxies could perfectly account for the gravitational effects we attribute to dark matter. They would be the ultimate macho, but made of a substance that is anything but ordinary. How could we possibly find something that does not interact with light? We watch for the moments when it bends light for us. This technique is called gravitational microlensing. If a dense, compact object like a primordial strangelet passes directly between Earth and a distant star, its gravity will act as a lens. It will briefly magnify and brighten the star's light in a distinctive, symmetric pattern. Surveys like the optical gravitational lensing experiment have monitored millions of stars for these telltale flashes. They have found events, but most can be explained by known objects like faint stars or planets. The hunt is for events with specific characteristics, very short durations, indicating an incredibly small lens, and a specific magnification curve that suggests an object with the density of a nuclear fragment, but on a planetary mass scale. A strangelet, depending on its size, could fit this profile perfectly. It would be a tiny, dark bullet of condensed quarks silently crossing our line of sight. Furthermore, these strangelets would not be harmless bystanders. If a cloud of them permeates our galaxy, they would occasionally collide with other objects. A direct hit on a neutron star would be a cosmic catastrophe. The strangelet, being the more stable form of matter, could begin converting the neutron star from the outside in. This process would release a burst of energy and potentially trigger a gamma-ray burst or an unusual, fast radio burst as the star's magnetic field is violently reconfigured. It could even transform an entire neutron star into a quark star in a relatively short astronomical timescale. So we are left with a profound and elegant idea. The quark stars we seek in the aftermath of supernova might be just one manifestation of strange matter. The true abundance of this substance could be far greater, frozen in time from the universe's infancy, and now constituting the invisible scaffolding of every galaxy. Solving the mystery of quark stars might not just add a new class of object to the heavens. It could provide the key to unlocking the nature of most of the matter in the cosmos. Deep within the theoretical heart of a quark star, matter may achieve a state of perfection so profound it defies earthly comparison. This is the predicted realm of color-superconductivity, a phenomenon where the star's core becomes not just a soup of free quarks, but a flawless quantum fluid with zero resistance. To grasp this, we must first understand a simpler wonder from our own world. In a regular superconductor, chilled to incredibly low temperatures, electrons overcome their mutual repulsion. They pair up into what are called Cooper pairs, allowing them to flow without any friction or loss of energy. It is a state of perfect electrical conduction. Now amplify that concept to an extreme beyond imagination. Inside a quark star, the density is so high that quarks are packed nearly touching. The temperature, while searing by our standards, is incredibly low relative to the titanic energy scales of quantum chromodynamics, the theory that governs quarks. Under these conditions, quarks are predicted to do something eerily similar to electrons. They form their own Cooper pairs, but because quarks carry a color charge, the source of the strong nuclear force, this paired state earns the name color superconductor. It is not just electrically superconducting, it is superconducting for the color force itself. The implications are staggering. This core would be a superfluid, meaning it flows without any viscosity, and a superconductor, expelling magnetic fields from its interior. It would be the most perfect fluid in the known universe. Theorists have mapped out possible phases for this exotic core with names that sound like science fiction. The most symmetric and stable is called the color flavor locked phase, or CFL. In this state, the pairing of quarks locks together their color charge and their flavor, that is, whether they are an up, down, or strange quark. This locking breaks symmetries in fundamental ways, potentially giving mass to some particles inside the core and leaving others massless. It is a complex, self-organizing quantum dance where the identities of the individual quarks become entangled in a collective, harmonious state. How would we ever detect such an abstract internal condition? The answer lies in the star's observable life story. A color superconducting core would fundamentally alter how the star cools and how its magnetic field dies. A normal neutron star cools primarily by emitting neutrinos, ghostly particles that stream out from its hot interior. In a CFL core, however, the pairing of quarks opens new channels for neutrino emission. Some models suggest this would make the star cool faster in its early life, like a hot stone plunged into water, while others indicate different phases could actually suppress cooling. By comparing the observed X-ray temperatures of very young, isolated neutron stars to cooling models, astronomers look for objects that are suspiciously cold or hot for their age, potential signposts of exotic physics at the core. Even more telling is the magnetic field. In a standard superconducting material, magnetic fields are expelled via the Meissner effect. They cannot penetrate the interior. A color superconducting quark core would do the same to its internal magnetic fields. This forces the star's entire magnetic field to be confined to its outer layers or its rigid crust. Over millennia, this trapped field would decay away much faster than a field anchored deep within a normal neutron star. So, if we find an old, dense stellar remnant that has a surprisingly weak magnetic field, it could be whispering a secret. It might be telling us that its heart is not made of neutrons, but of a perfect, frictionless quark superfluid, where the laws of physics have conspired to create a state of matter unlike any other. The concept of a perfect quantum fluid leads to one of the most practical and observable mysteries. How do magnetic fields behave in a star made of quarks? In our familiar world, magnetism arises from moving electric charges, like electrons swirling in a wire or the churning molten iron in Earth's core. In a neutron star, magnetism is a relic of the original star, amplified and frozen into the crust as the core collapsed. The most extreme version, a magnetar, possesses a field 1,000 trillion times stronger than Earth's, so powerful it can crack the star's crust and power immense bursts of X-rays and gamma rays. But what happens inside a quark star? The presence of a color superconducting core changes everything. A superconductor, by its very nature, expels magnetic fields. This is the Meissner effect. If you try to bring a magnet near a cold piece of superconducting material, it will float above it, suspended by the superconductor's refusal to let the magnetic field lines penetrate. In a quark star with a CFL core, the same principle should apply on a cosmic scale. The perfect quark fluid would expel any internal magnetic field, forcing it out into the star's outer layers or its rigid crust. This creates a bizarre internal architecture. The star's heart would be a magnetic void, a perfectly calm zone where magnetism cannot exist, while its skin, the crust, and any remaining neutron matter would be under immense magnetic stress, holding the entire star's field in a thin, intense shell. This concentration could, in theory, create surface magnetic fields even more powerful than those of magnetars. We could be looking at the ultimate magnetic engines in the universe. Yet the story might be even stranger. In some theoretical models, the magnetic field does not get fully expelled. Instead, it penetrates the superconducting core in the form of quantized vortices. Picture a massive hurricane, but instead of wind, its eye is a thin, microscopic tube of magnetic flux. The perfect superconducting fluid flows around these tubes without friction, but the tubes themselves are pinned, locked in place by imperfections in the star's structure. These vortices are not static. As the star spins, the vortices want to move outward, but if they are pinned, they build up tension. When that tension finally snaps, the vortices suddenly rearrange themselves in a catastrophic event. This microscopic process, happening across billions of vortices in the core, could be the hidden mechanism behind the giant flares and starquakes we see in magnetars. The energy released would be staggering, channeled along the magnetic field lines to the surface to produce the most powerful electromagnetic explosions since the Big Bang. So, the search for quark stars becomes a search for magnetic anomalies. Astronomers look for objects that have the explosive behavior of a magnetar, but with other characteristics that do not quite fit. Perhaps it cools too quickly, suggesting a different internal engine. Maybe its magnetic field decays away at an unusual rate, hinting that the field is not anchored deep within, but trapped in a fragile outer layer. Each X-ray flare, each soft gamma-ray burst is a potential clue. By decoding the light from these eruptions, their energy, duration, and afterglow, we are not just watching a star's tantrum. We are reverse engineering the physics of a quantum fluid under pressures that crush atoms into oblivion, listening for the telltale snap of magnetic vortices in a sea of free quarks. The magnetic fury of a magnetar is powered by its internal heat, a searing remnant of its violent birth. But that heat does not last forever. Every stellar corpse, no matter how exotic, must eventually cool and fade into the darkness of space. The rate at which this happens is not random. It is a precise clock, a thermal fingerprint that reveals the star's deepest secrets. This brings us to a powerful diagnostic tool and our next mystery, the cooling curve paradox. To understand it, we must first know how a normal neutron star sheds its heat. For the first million years of its life, the primary cooling mechanism is not light or X-rays streaming from its surface. It is the silent escape of neutrinos, those ghostly particles that barely interact with anything, streaming directly from the star's core into the cosmos. In a neutron star, this neutrino production happens through specific nuclear reactions like the modified Eerie process. Think of it as a slow, steady leak in a tire. It reliably lets the pressure out over a long period. Now, imagine if that tiny leak suddenly became a gaping hole. That is the difference if the core is made of quark matter. In a quark star core, the rules change completely. The free quarks can engage in something called the direct Eerie process. This is not a slow leak, it is a catastrophic venting. In this process, a down quark can directly convert into an up quark by emitting an electron and a neutrino, and the reactions can run in reverse with incredible efficiency. The neutrinos produced carry away staggering amounts of energy at a rate hundreds or even thousands of times faster than the modified Eerie process in a neutron star. A quark star would not just cool, it would plunge into a deep freeze with shocking speed. So how do we read this cosmic thermometer from 10,000 light-years away? Astronomers hunt for isolated neutron stars, those with no binary companion to accrete heating material, and take their temperature. They measure the X-rays coming from the star's hot surface. Then they estimate the star's age, often by measuring how fast its spin is slowing down or by tracing the expansion of the supernova remnant that birthed it. They plot these points, temperature versus age. This creates a cooling curve. For a population of normal neutron stars, the points should follow a predictable, gradual decline. But what if we find an outlier, a star that, for its estimated age, is suspiciously, inexplicably cold? It sits far below the expected curve on the graph, a lone data point whispering of a different physics. That star would be a prime candidate for harboring a quark core. Its chill would be the direct evidence of that hyper-efficient neutrino drain at its heart. The cooling curve paradox is a stark example of how the absence of heat can be the most revealing signal. We are not looking for a brilliant beacon, but for a shadow that cools too quickly, a void in the expected warmth of the universe, pointing silently toward the strange, perfect fluid within. The ultimate observational test for these cosmic phantoms is not written in their light or their heat, but in their fundamental proportions. Every star, no matter how exotic, obeys a simple rule. Its mass and its radius are locked in a gravitational embrace. For neutron stars, this relationship forms a predictable curve on a graph. As you add more mass, gravity pulls harder, forcing the star to become smaller and denser. But there is a limit, a point where adding more mass causes the star to collapse into a black hole. This is the neutron star mass radius curve, a boundary drawn by the equations of nuclear physics. Now draw another curve on that same graph. This one represents quark stars. For the same given mass, a pure quark star can be significantly smaller and denser than any neutron star could ever be. Its curve lies to the left in a region of the graph that should be empty according to conventional physics. This creates a clean, observational battleground. The mystery is which family of curves the real objects in the sky will follow. Are they all on the neutron star line, or do some of them stray into the forbidden zone, pointing toward a quark core? Measuring these properties from thousands of light-years away is a feat of cosmic engineering. Mass is the easier of the two. In a binary star system where a pulsar orbits a companion, its precise radio ticks act as a perfect clock. As the pulsar moves toward us, its pulses are squeezed together. As it moves away, they are stretched apart. By timing these ticks with exquisite accuracy over years, astronomers can map the orbit with surgical precision. From that orbital dance, they can directly weigh the stars. We now know of pulsars with masses approaching 2.5 times that of our Sun, pushing right against the theoretical limit for neutron stars. But mass alone does not tell the whole story. A 2-solar mass object could be a large, fluffy neutron star or a tiny, ultra-dense quark star. To tell them apart, you need the radius. This is where the challenge becomes immense. You are trying to measure the size of a city-sized object from a distance of interstellar space. One method is to study X-rays from a hotspot on the star's surface. As the star rotates, this bright region comes in and out of view, causing the total X-ray brightness to pulse. The shape and smoothness of that pulse encode information about the star's size. Another, more direct method comes from the aftermath of neutron-star mergers. When two of these objects collide, they can create a brief, super-hot remnant that emits a specific signature in X-rays and infrared light called a kilonova. The properties of that glow depend critically on the radius of the original stars. Bigger stars eject more material, creating a brighter, longer-lasting signal. Each new merger observed by gravitational wave detectors and telescopes adds another crucial data point. The data is now flooding in. Satellites like NAS, a neutron star interior composition explorer, or NICER, mounted on the International Space Station, are dedicated to this single task, measuring the radii of pulsars by staring at their X-ray hotspots. Its first major results have been tantalizing. For a famous pulsar called J0030 plus 0451, NICER measured a radius of about 13 kilometers, which fits comfortably within some models of neutron stars. But for another, PSR J0740 plus 6620, the data suggested a larger radius closer to 15 kilometers. This spread is the heart of the mystery. The data points are scattering across the graph, not neatly lining up on a single curve. Some theorists argue this scatter itself is a clue. Perhaps we are not looking at one type of object, but two. The smaller, denser points could be stars with large quark cores, while the larger ones are mostly neutron matter. The ultimate goal is to find an object with a mass so high and a radius so small that it simply cannot be explained by neutrons alone. That single, unambiguous data point, sitting defiantly in the quark star region of the mass-radius plot, would be the discovery of the century. It would be a direct measurement of a new state of matter. Every observation is a vote, and the universe is slowly, painstakingly filling out its ballot. The rigidity of a quark star's crust could be its most explosive feature. While neutron stars possess a crust of incredibly dense atomic nuclei, a lattice under immense strain, the surface of a true quark star might be something else entirely. It could be a crystalline layer of color-superconducting matter, a solid forged not from atoms but from quarks themselves. This is not a crust in any familiar sense. It is more like a single, gargantuan, perfect crystal, kilometers thick and under gravitational stress that makes diamond feel like soft clay. The fracture mechanics of such a substance are alien. A neutron star crust cracks and shifts in starquakes, releasing energy that causes the glitches we observe. But a quark star's crystalline crust would be far more rigid and brittle. The tensions building within it would be correspondingly greater. When it finally gives way, the energy released would be cataclysmic. The breaking of this ultra-dense lattice would not just nudge the star's rotation. It could shatter entire regions, sending powerful tremors through the star's interior and rippling out into space as bursts of high-frequency gravitational waves. These would not be the sweeping, low-frequency waves from merging black holes. They would be sharp, high-pitched chirps in the fabric of space-time, a seismic scream from a cracking crystal of condensed quarks. Even more directly, such a massive crustal failure could channel energy along magnetic field lines, erupting from the surface as a short, incredibly intense flash of gamma rays. We have seen such bursts from magnetars, but a quark starquake could produce a signal with a distinct fingerprint. The rise and fall of the gamma-ray emission, the spectrum of the light, and any associated X-ray afterglow would all carry the signature of the crust's unique composition and the depth of the fracture. For a neutron star, a quake might rearrange mountains a few centimeters high. For a quark star, it could be the equivalent of an entire continent shearing off and slamming back down, a tectonic event on a nuclear scale. Detecting the specific tremor of a color-superconducting crust would require a network of gravitational-wave observatories tuned to higher frequencies, a future capability that could turn every starquake in the galaxy into a detailed sonogram. Until then, we must listen to the gamma-ray sky, searching for an explosion that does not just shine, but rings with the clear, hard tone of breaking crystal. Gamma-ray bursts are not the only mysterious flashes lighting up the cosmos. In the vast, quiet darkness between galaxies, another phenomenon erupts with staggering power. For a few thousandths of a second, a point of radio light can outshine an entire galaxy, releasing more energy than our sun will emit in a century. These are fast radio bursts, and their origin is one of the most urgent puzzles in modern astronomy. While many theories exist, from colliding neutron stars to evaporating black holes, the extreme physics of quark stars offers a uniquely compelling, if speculative, solution. The central mystery is the engine. What natural process can concentrate such astronomical energy into a blink so brief? The answer may lie in the catastrophic failure of a color-superconducting crust. Picture that rigid, perfect crystal of quark matter under unimaginable strain. When it finally fractures, the energy released does not just shake the star, it violently shakes its magnetic field. Lines of magnetic force trapped in the crust are snapped and reconnected in an instant. This process of magnetic reconnection is a known powerhouse in our own sun's flares, but on a quark star, the scale is apocalyptic. The magnetic field involved could be a quadrillion times stronger. In that furious reconnection event, a vast sea of electrons is accelerated to nearly the speed of light. As these relativistic electrons spiral along the twisted field lines, they emit a coherent, lighthouse-like beam of radio waves in a process called synchrotron maser emission. The entire event, the crack, the snap, the beam, could be over in milliseconds, matching the duration of an FRB perfectly. But there is another, even more exotic possibility involving the strange matter hypothesis itself. Imagine a wandering strangelet, a primordial nugget from the dawn of time, finally meeting its end. It drifts through the halo of a distant galaxy and plunges into the magnetosphere of a neutron star. The moment it makes contact, a conversion begins. The strangelet, being the more stable state of matter, starts to transmute the neutron star's surface. This is not a slow infection, but a sudden, runaway reaction. As the strangelet burrows in, it releases a colossal burst of energy, not from nuclear fusion, but from the binding energy of quarks being rearranged into their perfect, stable configuration. This energy floods into the star's immense magnetic field, triggering a shock wave that races outward and produces a brilliant, one-time radio flash. This model could explain the non-repeating FRBs, single catastrophic events that never happen again. For the repeating FRBs, those that flash over and over from the same patch of sky, the quark starquake model fits beautifully. The crust, under constant strain from a super-strong magnetic field or a slowing spin, could fracture repeatedly, each crack producing a new burst. The energy scales match. To power an FRB from a distant galaxy, you need an engine that can convert a significant fraction of a solar mass into pure radio energy with almost perfect efficiency. The binding energy released when a cubic kilometer of neutron star crust collapses into strange matter, or when a continent-sized quark crystal shears off, provides that fuel. It is a reservoir of energy far beyond chemical or even nuclear processes, tapping directly into the fundamental forces that hold quarks together. While magnetars remain strong candidates, a quark star or a strange-elit interaction represents a more extreme version of the same idea, a celestial object where matter itself is in its ultimate, most unstable configuration, forever on the verge of releasing a scream of energy that echoes across the universe. Every time a new FRB is detected with its unique polarization, its dispersion measure tracing through intergalactic plasma, astronomers are not just plotting a point on a map. They are potentially listening to the sound of a quark star's crust breaking, or the final signal of a strange-elit rewriting a star's surface, a brief, brilliant testament to the strange and violent states of matter hidden in the dark. That final, brilliant flash of a fast radio burst may be the death rattle of a strange-elit, but what about the first sound a quark star ever makes? There is a hidden moment in the death of the most massive stars, a theoretical instant so brief and violent we have never seen it. This is the birth cry of a quark star. Picture the final milliseconds of a supernova. The iron core collapses, rebounds in a shockwave, and leaves behind a hot, young neutron star. But for some, the story does not end there. The newborn neutron star is under unimaginable pressure, still cooling and settling. If its mass is just right, the inward crush of gravity may win a second, more fundamental victory. Deep in the core, the sea of neutrons reaches a breaking point. In a catastrophic phase transition, the neutrons dissolve. Their boundaries vanish, and the quarks inside are liberated, merging into a soup of up, down, and strange quarks. The entire core undergoes a second collapse. It is not the star falling in on itself, but the very particles that compose it undergoing a radical rearrangement. This collapse happens in a heartbeat, perhaps in less than a millisecond, and like any violent birth, it would scream. The energy released in this quark nova would be staggering, not from nuclear fusion, but from the binding energy of quarks as they settle into their new, perfect state. Most of that energy would flood out in two invisible forms. First, a torrent of neutrinos. A supernova already produces a legendary neutrino burst, but a second collapse would unleash another distinct pulse. It would be a sharper, hotter blast of these ghostly particles, a specific fingerprint in the neutrino data signaling that something stranger than a neutron star had just been born. Second, and perhaps more detectable, would be a burst of gravitational waves. This is not the sweeping chirp of two objects merging. This would be a short, sharp pop in the fabric of spacetime. As the core's geometry violently shifts from a sphere of neutrons to a denser sphere of quark matter, it would ring like a bell struck by a hammer, emitting gravitational waves at a characteristic frequency. The challenge is catching this signal amidst the chaos. If it happens moments after the initial supernova, its gravitational wave pop would be buried in the longer, messier signal of the core collapse itself. Separating it would require exquisite precision, but there is another, more tantalizing possibility. What if the second collapse is delayed? Some models suggest it could happen years, decades, or even centuries after the supernova, once the neutron star has cooled sufficiently for the phase transition to finally trigger. In that scenario, we would witness a standalone event. A known, quiet neutron star, a steady pulsar we have been watching for years, could suddenly vanish from our radio telescopes. In its place, a new, slightly smaller and denser object would appear, perhaps with a different spin or a weaker magnetic field. And at the moment of its transformation, space itself would ring with that singular gravitational wave pop, a clean signal with no supernova background noise to hide it. This birth cry remains one of the great unobserved predictions of astrophysics. We have the equations that say it should happen. We have the detectors like LIGO, Virgo, and future space-based observatories that could, in theory, hear it. But the universe has yet to perform this particular act in our viewing. It is a hidden chapter in the life cycle of matter, a secret transition between two impossible states. To witness it would be to catch the universe in the act of rewriting its own rules, to hear the first sound of a new form of matter announcing its existence to the cosmos. That birth cry of a new state of matter leads to a question that haunts the edges of this entire field, a mystery that blends profound physics with a touch of cosmic dread. This is the stranger at danger, a debate that asks if our very experiments could unravel reality. The core idea is as elegant as it is unsettling. If the strange matter hypothesis is correct, and a bound state of up, down, and strange quarks is the true ground state of matter, then a speck of this substance, a strangelet, would be more stable than the iron in the Earth's core. It would represent matter in its final, perfected form. The theoretical danger emerges from a property called catalytic conversion. If a strangelet came into contact with a normal atomic nucleus, like a proton or a neutron, it could theoretically convert that nucleus into more strange matter. The process would release energy and bind the new particles to the growing strangelet. In a catastrophic chain reaction, a single seed could, in principle, convert an entire planet, star, or more, rewriting the material universe from the inside out into an ever-expanding blob of hyper-dense strange matter. It is the ultimate physics nightmare scenario where discovery itself could mean oblivion. This speculation naturally turned toward humanity's most powerful tools, particle colliders. When the Large Hadron Collider was preparing for its first high-energy collisions, a public discussion emerged. Could the unprecedented energies smashing protons together at nearly the speed of light create a microscopic strangelet? And if one were created, could it begin this apocalyptic conversion process? The scientific community took these questions seriously. Multiple, independent safety reviews were conducted, examining the data from decades of cosmic ray collisions. The reasoning was straightforward and conclusive. Our planet and every celestial body in the cosmos has been bombarded by cosmic rays with energies far exceeding anything the Large Hadron Collider can produce for billions of years. These natural collisions are happening constantly in our upper atmosphere and on the surfaces of the Moon and Mars. If the creation of a dangerous, stable strangelet were possible, it would have been triggered naturally long ago in the dense matter of a neutron star or in these relentless cosmic impacts. The fact that Earth and other astronomical bodies still exist composed of normal matter is the most powerful evidence that such an event is either impossible or so incredibly rare that the statistical risk is effectively zero. The safety assessments unanimously concluded that particle colliders pose no threat. Yet, the mystery does not vanish with that reassurance, it simply deepens and shifts. The debate over strangelet danger is not really about the safety of our machines. It is a proxy for a far more profound question about the fundamental stability of the vacuum of space itself. Physicists call this the concept of the false vacuum. Our universe, with its specific laws, constants, and states of matter like protons and neutrons, might not be in the absolute lowest energy state. It could be in a metastable valley, a temporary resting place, a sufficiently energetic event, or the introduction of a true ground state material like strange matter could theoretically provide a quantum tunnel or a catalyst to push the entire region of space into a lower energy configuration. This transition would spread at the speed of light, rewriting the laws of physics in its wake. In this grand cosmological view, the strangelet is not just a dangerous particle. It is a potential key to a different universe. The mystery, then, is this: are we and everything we see living in a cosmic bubble of temporary stability, surrounded by a vacuum that yearns for a different, more perfect form? Or is our matter truly the final, stable state? The fact that we have to ask that the equations allow for such a terrifying possibility is what keeps this idea alive in the halls of theoretical physics, a chilling reminder that our understanding of reality's bedrock is still under construction. The stability of our entire material universe hinges on a force we barely understand in its most extreme form. This is the quantum chromodynamics challenge, the fundamental reason why quark stars remain theoretical phantoms. At its heart, every mystery we have explored, from strange matter's stability to color superconductivity, stems from our inability to solve the equations governing the strong nuclear force under conditions of unimaginable density. Quantum chromodynamics, or QCD, is the triumphant theory that describes how quarks interact, bound together by particles called gluons. It works beautifully to explain the protons and neutrons inside every atom. But inside a quark star, the rules of the game change completely. The density is so high that quarks are no longer neatly confined inside individual protons and neutrons. They break free, creating a seething, ultra-dense soup where the distances between quarks are almost zero. Under these conditions, the mathematics of QCD becomes intractable. The equations are so complex and non-linear that they simply cannot be solved with pencil and paper. This is the terra incognita of the nuclear matter phase diagram, a vast map of how matter behaves under different temperatures and densities. We know the familiar territories well, the gas of atoms here, the liquid of nuclear matter there. We have charted the neutron-star region through observation and theory. But the quark matter phase exists in a region of extreme density and relatively low temperature that our mathematical tools cannot reliably map. It is a blank space on the chart, labeled only with question marks. To probe this unknown, physicists have developed two powerful complementary tools. The first is the supercomputer. Using a technique called lattice QCD, they simulate a tiny, finite chunk of spacetime as a four-dimensional grid. They place quarks and gluons on this lattice and let the rules of quantum chromodynamics play out through immense computation. This method works brilliantly for studying the high-temperature quark-gluon plasma, similar to conditions just after the Big Bang, which we can briefly create in particle colliders. But for the cold, ultra-dense environment of a quark star, lattice QCD hits a wall. The calculations become plagued by something called the sign problem, a mathematical instability that makes the results too noisy to trust. It is like trying to hear a whisper in a hurricane of static. So, if supercomputers cannot take us there, we must use the universe itself as our laboratory. This is where the second tool comes in: astrophysical observation. Every neutron star or potential quark star we detect is a natural experiment, a data point placed somewhere on that elusive phase diagram. Its mass, its radius, its cooling rate, the way it glitches or flares, these are all outputs from the unsolved equations of QCD under extreme conditions. By collecting enough of these cosmic data points, we can work backwards. We can say, if this star has a radius of 12 kilometers and glitches in this specific pattern, what does that tell us about the equation of state? Which theoretical model of dense matter does it support? Each observation places a constraint, ruling out vast swaths of possible theories and narrowing the path toward truth. It is a dialogue between the sky and the supercomputer. The observations tell the theorists where to look and what to simulate next. The simulations, in turn, suggest new signatures for the observers to hunt for. A strange cooling curve here might prompt a new lattice calculation. A puzzling gravitational-wave signal there might refine our models of hybrid stars. Together, they are slowly sketching the borders of that unknown territory on the phase diagram. The ultimate goal is to find the critical line, the boundary where neutrons dissolve and quarks reign supreme. To cross that line would be to finally solve the strong force in its ultimate domain, unlocking not just the secret of quark stars, but a fundamental chapter in the story of matter itself. The blank spaces on the quantum chromodynamics map can only be filled by listening to the universe with every sense we possess. This is the immense promise of multi-messenger-astronomy, and quark stars are its perfect, elusive target. For centuries, we have studied the cosmos with light alone, from radio whispers to gamma-ray screams. But the most profound secrets are often broadcast on channels we are only now learning to tune. To find a quark star, we must become universal polyglots, fluent in the language of gravitational waves. the dialect of neutrinos, the song of cosmic rays, and the ancient script of light. A single messenger can hint at an anomaly, but a chorus of them, singing in unison about the same event, can reveal a truth no single signal could ever prove. Imagine a ripple in spacetime is detected by observatories like LIGO and Virgo. The signal has the characteristic chirp of two ultra-dense objects merging, but the details are off. The tidal deformability is too low, suggesting objects incredibly stiff and small. Seconds later, a space-based gamma-ray telescope like Fermi or Swift records a brilliant, short burst from the same patch of sky. The burst's energy spectrum is unusual, lacking the telltale signs of certain nuclear processes. Then, deep underground detectors like super-camiok and/or the future hyper-camiok and register a distinct pulse of neutrinos, not with the smooth profile of a supernova, but with a sharp, hot spike that suggests a sudden, profound phase transition in dense matter. Finally, as the aftermath unfolds, traditional telescopes see a kilonova glow whose color and evolution point to an exotic composition of ejected material, perhaps rich in strange quarks. This coordinated symphony of signals would be the smoking gun. The gravitational waves tell us about the object's bulk properties and internal stiffness. The gamma rays tell us about the violent, magnetic aftermath of their collision. The neutrinos carry a direct, unedited report from the heart of the cataclysm, revealing the nuclear reactions and energy release at the moment of merger. The optical and infrared light from the kilonova acts as a forensic analysis of the debris, revealing the chemical elements forged in the explosion. A coincidence of just two of these messengers would be compelling. A convergence of 3 or 4 would be revolutionary. It would allow us to cross-check every model to rule out alternatives with overwhelming confidence. We would not just infer the presence of quark matter, we would measure its properties from multiple, independent angles, building a three-dimensional picture of an object we could never see. This multi-messenger approach transforms the search from a guessing game into a forensic investigation. Each type of observation covers for the weaknesses of the others. Gravitational waves are pristine carriers of information but poor at pinpointing location. Light gives us a precise sky address but can be obscured or mimicked. Neutrinos travel straight through anything but are devilishly hard to catch in meaningful numbers. Together, they compensate for each other's blind spots. A single, quiet quark star drifting alone might forever hide its nature, but in the most violent acts of cosmic destruction, the mergers, the quakes, the transformations, it may finally be forced to reveal its secret in a language so rich and multifaceted that we cannot possibly mistake its meaning. The next great discovery in astrophysics may not arrive as a single brilliant flash in a telescope, but as a synchronized alarm across a global network of instruments, all ringing at once to announce that we have finally heard the universe speaking in its full, strange voice. The search for a cosmic symphony of signals often begins with a single, quiet note of discord. History is filled with stellar corpses that refuse to fit the mold, their subtle anomalies whispering of a stranger truth. Among these historical candidates, one object stands out with a particularly cold and ancient story. It is the remnant of a supernova recorded by Chinese and Japanese astronomers in the year 1181. A guest star that shone for 6 months in the constellation Cassiopeia before fading from view. Today, we know it as 3C58, and its modern appearance holds a chilling clue. Observations from the Chandra X-ray Observatory reveal a pulsar at its heart, spinning 15 times every second. Yet, for an object just over 800 years old, it is far too cold. Based on standard neutron-star cooling models, 3C58 should still be a seething ember glowing fiercely in X-rays. Instead, its temperature suggests a rapid and profound cooling, as if its internal heat was drained away through some hyper-efficient process. This discrepancy is the core of the mystery. Could the pulsar in 3C58 be cooling so quickly because it harbors a quark matter core? The direct Urca process, that catastrophic neutrino vent possible only with free quarks, would provide the perfect explanation. It would be like comparing two cups of freshly boiled water. One left on a counter cools slowly, but the other, poured through a fine sieve, loses its heat in an instant. The quark core hypothesis elegantly turns an anomaly into a prediction. For years, 3C58 was heralded as another strong candidate for an exotic interior, its unexpected chill pointing toward a fundamental phase transition at its heart. However, as with RxJ1856, new data and more nuanced models have complicated the picture. The cold temperature might not require strange physics at all. Alternative explanations emerged. Perhaps the pulsar's magnetic field is stronger than initially measured, and its decay is helping to cool the surface faster. Maybe the star has an unusually light element atmosphere like carbon, which radiates heat more efficiently than the standard hydrogen or helium models assume. Or the initial supernova explosion itself could have been less energetic, leaving the newborn neutron star with a lower birth temperature to begin with. Each of these scenarios can, to varying degrees, explain the observed data without invoking a quark core. The story of 3C58 is a perfect case study in how scientific interpretation evolves. It is not a story of a right answer being replaced by a wrong one, but of a simple, elegant hypothesis being challenged by a more complex and often more mundane reality. The object remains a compelling puzzle, but its low temperature is no longer a clear signal. It is a possibility, one thread in a larger tapestry of evidence. This pattern of re-evaluation is common. Another historical candidate, the compact central object in the supernova remnant Cassiopeia A, also shows puzzlingly rapid cooling. Data from Chandra suggested its temperature dropped by about 4% over a mere decade, a change far too swift for standard models. Again, theorists propose that a transition to a superfluid or superconducting state in the core, possibly involving quark matter, could explain the sudden chill. Yet again, other groups propose that changes in the star's solid crust or its magnetic field could produce a similar cooling profile. These historical candidates teach us a crucial lesson about cosmic detective work. An anomaly is a starting point, not a conclusion. A single odd measurement, like a surprisingly cold temperature, is a clue that points in many directions. It invites us to build better models, to collect more precise data, and to consider the full spectrum of physics from the familiar to the fantastical. The pulsar in 3C58 may or may not hide a quark core, but its enduring mystery and the rigorous debate it sparks ensures that this ancient stellar remnant remains a vital touchstone. It reminds us that the universe's greatest secrets are not simply handed to us. They are wrestled from the data through a long and careful process of questioning every assumption, where today's leading candidate can become tomorrow's cautionary tale, all in the relentless pursuit of a deeper, stranger truth. Every stellar corpse, every flash from the void, is a single point plotted on a cosmic map we are only beginning to draw. This map is not of stars and galaxies, but of matter itself, charting its behavior under every conceivable condition of heat and pressure. It is the phase diagram of quantum chromodynamics, and it holds the ultimate context for our entire search. Think of the most familiar phase diagram you know, water. At standard pressure, it tells you where you will find solid ice, liquid water, and gaseous steam, depending on the temperature. The QCD phase diagram is that concept, but for the fundamental building blocks of reality. Its axes are not simple temperature and pressure, but temperature and baryon density, a measure of how tightly you pack particles like protons and neutrons. On this vast and theoretical chart, our everyday world occupies a tiny, quiet corner. We live in the realm of hadronic matter, where quarks are forever locked inside protons and neutrons, the building blocks of atoms. This is the ice phase of the strong force. Now turn the temperature up to trillions of degrees, as it was a microsecond after the Big Bang, or as we briefly do in particle colliders. At these extremes, the bonds shatter. Quarks and gluons break free from their confinement, swirling in a primordial soup known as the quark-gluon plasma. This is the steam phase, a seething, chaotic state we have managed to recreate for fleeting instants, but the diagram has other, far stranger territories. At incredibly high densities but relatively low temperatures, matter is predicted to enter phases of color-superconductivity, where quarks pair up and flow without resistance. And it is here, in this high-density, low-temperature corner of the map, that we find the theoretical home of quark stars and strange matter. This region is not just unknown, it is fundamentally inaccessible to any Earth-bound experiment. Our most powerful colliders can create the high temperatures of the early universe, but they cannot also generate the crushing, sustained densities needed to probe this cold, dense frontier. We cannot squeeze a city's worth of mass into a laboratory sphere. This is why every potential quark star is more than just a celestial oddity. It is a natural, pre-built laboratory, operating under conditions we can only dream of replicating. Each observation, a precise radius measurement from NICER, a glitch pattern from a pulsar, a gravitational wave chirp from a merger, is a single, precious data point we can place somewhere on this blank section of the diagram. Is the object stiff or soft? Does it cool quickly or slowly? The answers tell us which theoretical curve it falls on, effectively drawing the boundary lines between neutron matter and quark matter. When we combine enough of these cosmic data points, we begin to sketch the shape of reality in its most extreme form. We are mapping the landscape of the strong nuclear force itself, learning how it behaves when matter is compressed to the absolute limit. Every anomaly, every candidate is a star on this map, guiding us toward the true geography of the quantum world. To find a quark star would be to finally plant a flag in this uncharted territory, proving that nature not only allows this exotic state but chooses to build with it. It would complete a chapter in the story of matter that began with the quark-gluon plasma of the Big Bang and may end with color superconducting crystals drifting in the dark. Our search among the stars is, in truth, a quest to complete the universe's own instruction manual, reading the pages written in density and decay. But a solitary quark star is only half the story. The universe loves a partnership, and when these exotic objects find themselves locked in a gravitational dance with another star, the results can be even more spectacular and revealing. The behavior of a quark star in a binary system could broadcast its identity in ways a lone star never could. Imagine a classic X-ray binary where a dense stellar remnant pulls a stream of gas from a bloated companion star. This material, rich in hydrogen and helium, spirals down onto the remnant's surface, compressing and heating until it undergoes runaway nuclear fusion. On a neutron star, this creates a type I X-ray burst, a brilliant flash that lasts for seconds as the accumulated fuel detonates in a thermonuclear firestorm. But what if the surface it falls onto is not a neutron star's crust, but the rigid, crystalline skin of a quark star? The physics of ignition would be fundamentally altered. The quark star's surface is far denser and potentially smoother, lacking the magnetic pockets and crustal irregularities of a neutron star. The accreted fuel might spread differently, burn at a different temperature, or even fail to ignite in the familiar pattern. We could see X-ray bursts with unusual durations, energies, or recurrence times, subtle anomalies in the flashbulb pop of a cosmic explosion that point to a stranger surface beneath. The real drama, however, may not happen on the surface but deep within. This is the concept of an accretion-induced phase transition. Picture a quark star in a binary, slowly and steadily feeding on its companion for millions of years. With each mouthful of stolen matter, its mass increases, gravity's grip tightens. For a neutron star, this process has a known limit, the Tolman-Oppenheimer-Volkoff limit, the maximum mass it can support before collapsing into a black hole. But a quark star might have a different path. As its mass creeps upward, the pressure in its core mounts. It may already have a small quark core, a hybrid star biding its time. The added weight could push it over a critical threshold, triggering a delayed but catastrophic transformation. The entire star, or a significant portion of its interior, could undergo a sudden, wholesale transition from neutron matter to quark matter. This would be a quark nova, not from a supernova's aftermath, but from a slow, gluttonous feast. The energy released from this fundamental rearrangement of particles would be titanic. It could blow away the star's outer layers in a spectacular second explosion, ejecting material rich in strange quarks and creating a unique, short-lived supernova-like event within the binary system. We would witness a star apparently rebelling against its own growth, erupting in a brilliant flash as its very substance is rewritten. This leads to the ultimate binary finale, the merger. We have detected gravitational waves from neutron-star collisions, events that forge gold and platinum in their debris. But what is the fate of two merging quark stars? The outcome hinges on a critical and unknown number, the maximum mass of a stable quark star. If quark stars can support more mass against gravity than neutron stars can, then their merger could create something extraordinary. Instead of immediately forming a black hole, the combined object might briefly exist as a hypermassive quark star, a rapidly spinning, monstrous blob of strange matter sustained by its own incredible rotation. This object would be a transient wonder, living for perhaps hundreds of milliseconds before centrifugal support fails and it too collapses. That brief window, however, would be a frenzy of activity. Its oscillations would pump out high-frequency gravitational waves, a unique siren song of ultra-dense matter. It might even power a prolonged gamma-ray burst or an extraordinarily bright kilonova as its quark-rich exterior is blown away in the turbulent merger. Alternatively, if the total mass is simply too great, the merger would proceed directly to a black hole, but the path there would still bear the signature of quark matter. The in-spiral would be different, the last orbits before the plunge altered by the star's exceptional stiffness. The gravitational wave signal would lack the tidal stretching characteristic of softer neutron stars, ending in a sharper, more abrupt silence. By comparing future merger signals to our growing library of simulations, we may one day hear the distinct hard ring of two quark stars meeting, a collision that sounds not like a splash but like the striking of two cosmic anvils. The ultimate fate of a quark star presses against the most profound boundary in physics. It exists at the very precipice of becoming a black hole, a final stable outpost before matter vanishes behind an event horizon forever. This precarious position places it at the heart of a modern physics war, the black hole information paradox. At its core, this paradox is a conflict between the two great pillars of modern physics. General relativity, Einstein's theory of gravity, tells us that anything that crosses a black hole's event horizon is lost forever. The black hole's properties are defined only by its mass, spin, and charge. All other information about what fell in the type of particle, its quantum state, its history, is seemingly erased from the universe. Quantum mechanics, however, states with absolute certainty that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. This is a fundamental tenet of reality. So, what happens to the information of a book, a star, or a person that falls into a black hole? Does it vanish, violating quantum law? Or is it somehow preserved, challenging our view of gravity? For decades, this has been an untestable philosophical puzzle. But a quark star, if it exists, offers a potential escape route, a physical object that might sidestep the paradox entirely. Unlike a black hole, a quark star is predicted to have a physical surface. It is not a point of no return, but an actual boundary of ultra-dense matter. When material falls onto it, it does not disappear into a singularity. It impacts a solid or perhaps a color-superconducting crust. The information contained in that material, the arrangement of its atoms, their quantum spins, would not be lost. It would be imprinted onto the star's surface in some immensely complex, scrambled way, and then potentially radiated away over eons as the star cools and emits particles. In this view, a quark star could be nature's compromise. It is the densest possible object that still maintains a physical structure, a last bastion where information is preserved. It represents the final victory of quantum mechanics over gravity's destructive urge, a celestial object so dense it bends space-time to its limit, but refuses to break the universe's most sacred rule. Studying how a quark star behaves as it approaches its maximum mass could therefore be a direct window into quantum gravity. Does it develop strange thermodynamic properties? Does its surface exhibit quantum effects on a macroscopic scale, observing the final moments before a collapse? The last glitches, the final cooling pulses, the gravitational waves emitted as it teeters on the edge, could reveal the precise mechanism by which information is preserved or lost. It could show us the moment when matter chooses between two destinies, to become a strange, information-preserving quark star, or to cross the line and become an information-destroying black hole. The search for quark stars is no longer just about cataloging exotic objects. It is a direct assault on one of the deepest mysteries of existence, probing the very rules that govern reality at its most extreme. The profound mysteries we have explored are not just cosmic secrets. They are, in many ways, reflections of our own technological limits. We are trying to hear a whisper from across a continent, using ears still learning how to listen. Every unanswered question about quark stars and strange matter is a direct challenge to the cutting edge of our engineering and our ingenuity. The first and perhaps most persistent challenge is simply seeing them. Or more precisely, measuring their size. Determining the radius of a city-sized object 10,000 light-years away with an X-ray telescope is an exercise in exquisite frustration. Instruments like NICER, while revolutionary, are pushing against fundamental barriers. They rely on the faint, pulsing X-rays from hotspots on the star's surface. To translate those flickers into a precise radius, we must make a series of assumptions. We must model the star's atmosphere, its magnetic field geometry, and the exact shape and temperature of the hotspots. A slight error in any of these assumptions can change the radius measurement by a kilometer or more. It is like trying to measure the exact diameter of a distant lighthouse by the flicker of its lamp, while a thick, shifting fog obscures the view. You might get a rough estimate, but the precise number remains maddeningly elusive. This is why the mass radius plot is still a scatter of points, not a clean line. Each point has an error bar, a zone of uncertainty that often overlaps both neutron star and quark star predictions. We are seeing the data through a blurry lens. The next generation of X-ray observatories, like the European Space Agency's Athena mission, promises to sharpen that lens dramatically. With a collecting area over 100 times larger than current telescopes, Athena will capture far more X-ray photons, providing a clearer, more detailed picture of those hot spots. It will be like upgrading from a grainy photograph to a high-resolution scan, finally allowing us to shrink those error bars and see which theoretical curve the stars truly follow. The gravitational wave window faces a different but equally daunting sensitivity challenge. Current detectors like LIGO and Virgo are marvels, but they are tuned to hear the mergers of black holes and neutron stars. The subtle differences in the gravitational wave chirp that would betray a quark star's incredible stiffness, the tiny lack of tidal stretching in the final orbits, is an extremely faint signal buried in the noise. Discerning it requires a level of precision we are only now approaching. Future upgrades like the planned A+ upgrade for LIGO and the next-generation Cosmic Explorer and Einstein telescope projects will be 10 times more sensitive. They will listen deeper into the universe and hear higher frequencies. This is crucial because the ring down of a hypermassive quark star or the high-frequency pop of a quark nova lives in a part of the gravitational wave spectrum our current instruments barely perceive. These future observatories will turn the faintest cosmic whispers into audible conversations, allowing us to measure tidal deformability with such precision that the difference between a neutron star and a quark star will become unmistakable. Then there is the hunt for the strangelet itself. Identifying a nugget of strange matter in the cosmic ray flux is a needle in a haystack problem of galactic proportions. Our detectors, like the alpha magnetic spectrometer, are incredible feats of engineering in the harsh environment of space, but they are limited by exposure time and resolution. A strangelet, if it exists, would be incredibly rare. We need to collect more particles over longer periods with even greater precision to distinguish its subtle signature from background noise and rare nuclear isotopes. New generations of cosmic ray detectors, possibly placed on high-altitude balloons or dedicated satellites with larger acceptance areas and more sophisticated particle identification systems, are the only way forward. They must act as both microscope and filter, sifting through billions of mundane particles to find the one that behaves just a little bit wrong, the one whose charge-to-mass ratio or decay pattern hints at a core made not of protons and neutrons but of free quarks. These limitations are not failures, they are the frontier. Each mystery persists because the universe has set a higher bar for discovery, demanding that we build better tools to ask better questions. The enhanced LIGO, the Athena Observatory, the next cosmic ray hunter, these are not just new machines. They are the keys we are forging to unlock doors we have only been able to peer beneath. They represent our species' stubborn refusal to let distance and density have the final word, a commitment to reach across the light years and finally feel the texture of the universe's strangest matter. The final and perhaps most haunting mystery is not about how these stars live, but how they end. What is the ultimate fate of a quark star over the unimaginable spans of cosmic time? Does it simply fade into a cold, dark crystal, or does it hold within its perfect form a seed of its own destruction? The answer hinges on the absolute stability of strange matter itself. If it is truly the ground state, then a quark star is the final, eternal resting place for matter. No further decay is possible. It has reached the end of the line. In this scenario, as the eons pass, the star would simply cool. Its furious neutrino emission would cease. Its X-ray glow would dim to nothing. After trillions of years, long after the last normal stars have burned out, the quark star would remain. It would be a pitch-black nugget of perfect strange matter, a cold, dense fossil drifting through an expanding, darkened universe. Astronomers sometimes call these theoretical relics strange dwarfs or quark nuggets, the ultimate end product of stellar evolution, outliving even the black holes that may slowly evaporate via Hawking radiation. They would be the last durable structures in a dying cosmos, monuments to a state of matter so stable it transcends time, yet stability is not guaranteed. The equations allow for another, more dramatic finale. Suppose strange matter is not perfectly stable, but only metastable like a diamond. It holds together under immense pressure, but given enough time, cosmological time, or the right trigger, it could decay. The quarks within might undergo a slow quantum tunneling process, transforming into something else entirely, perhaps even dissolving into a burst of lighter particles. This process would be unimaginably slow, perhaps taking googles of years, but it would mean that even these perfect objects have an expiration date. They would not fade, but fizzle, their immense mass energy gradually leaking back into the universe in a final, slow-motion sigh. There is a third and more violent destiny tied directly to their environment. A solitary quark star may be eternal, but the universe is rarely so lonely. If it orbits in a binary system, it faces a constant temptation. As it accretes matter from its companion, its mass slowly increases. Each new gram tightens gravity's grip. There is a critical threshold, a maximum mass for a quark star, just as there is for neutron stars. Cross that line, and no known force in the universe can prevent total collapse. The quark star would not simply compact further. It would undergo a catastrophic gravitational failure. In a final, silent event that emits one last, sharp pop of gravitational waves, the entire structure would vanish behind an event horizon. The ultimate fate of a quark star, then, could be to become the very thing it defied, a black hole. Its existence would have been a prolonged defiance of gravity's ultimate wish, a centuries-long or billion-year-long hesitation at the precipice before finally taking the final step into the dark. This ultimate mystery wraps every other question into one. It asks what matter truly wants to be when left alone with eternity. Is the universe's preference for a cold, stable crystal of quarks, or for the empty mystery of a singularity? The lifespan of a quark star is a direct experiment on the fundamental forces, running in slow motion across the lifetime of the cosmos. To find one is to find a clock that may never stop ticking, or one that is counting down to an end we cannot yet foresee. It forces us to look beyond the brilliant violence of their birth and the subtle signals of their middle age, to ponder the final, dark silence that awaits all things, and to wonder what form perfection takes when the lights of the universe finally go out. From the silent fate of a single quark star, we pull back to see the entire journey. We have ventured from the theoretical edge of existence through violent stellar births and catastrophic collisions into the quantum heart of matter itself. 25 interwoven mysteries have guided us, each one a thread in a tapestry that connects the unimaginably small to the incomprehensibly vast. Quark stars and strange matter are not merely hypothetical objects. They are a thrilling nexus, a point where particle physics, astrophysics, and cosmology converge in a single, profound question. They force us to test our theories of the strong nuclear force against the brutal reality of collapsing stellar cores. They challenge our understanding of stability, suggesting that the ground beneath our feet and the atoms in our bodies might be a temporary arrangement in a universe yearning for a more perfect state. They offer potential explanations for the cosmos's brightest flashes and its darkest missing mass, and they press directly against the final boundary of reality, the event horizon of a black hole, probing the ultimate fate of information itself. This pursuit, whether it ends in triumphant confirmation or in elegant dismissal, is never a failure. The value is in the chase. Every anomalous cooling curve, every puzzling glitch, every subtle gravitational wave signature forces us to refine our models, to question our assumptions, and to invent new ways of seeing. We have mapped the phase diagram of quantum chromodynamics with data points from across the galaxy. We have built detectors to listen to the ringing of space-time and sift through the rain of cosmic rays. We have learned that the universe is far stranger, more creative, and more violent than we ever dreamed. The next chapter in this story is being written right now, not in textbooks, but in the data streams pouring in from instruments around the globe and in orbit. The NICER telescope's next radius measurement, LIGO next gravitational wave chirp, a space station detector's next anomalous particle hit. Any one of these could be the clue that changes everything. The discovery that finally confirms a quark star or definitively rules it out will not be an end. It will be a new beginning, opening doors to deeper mysteries we have not yet even learned to ask. So the next time you look up at the night sky, remember that the darkness is not empty. It is a dynamic, evolving laboratory of extreme physics. Within that vastness, stellar corpses may be hiding the universe's most perfect substance and the answers to our most fundamental questions. Stay curious, follow the news from those great observatories. The greatest discoveries are not behind us. They are out there, waiting in the data, in the next flash of light, in the next ripple in space-time for us to find them.